Welcome back. In the last part of this section, we're going to talk about the second derivative test, which is another way for us to tell if we've got a relative maximum or a relative minimum for our function. So first, the preamble for this theorem, we've got a function, and we have a first derivative that's equal to 0 at this point. So first off, we know that that's a critical number, c is, and our second derivative exists on an open interval containing c. So already quite a few side conditions. We have to have found ourselves a critical number. It has to be a critical number because the derivative is 0, not because the derivative is undefined. That's number one. Our second derivative also needs to exist. And then finally, if all of that conditions are being met, then we can check to see if we have a relative max or a relative minimum by looking at the second derivative. And if our second derivative is positive, if we are concave upwards, then you've got a relative minimum at that point. And if you're concave downward, then you've got a relative maximum at that point. And the reason for the test, why it seems to work nicely for us, is because, again, the first derivative being equal to 0 means we have a horizontal tangent line. So we have to be at some sort of a place where our tangent line is horizontal. And of course, maximum and minimum places, those are places where we have horizontal tangent lines. And then finally, after that, if we're thinking about concavity and how does that play into things, if you are a minimum, then your concavity for that local minimum should be a concave up kind of a shape. And if you are a maximum, then your concavity should be a concave down kind of a shape. And of course, second derivative being positive means we're concave up, and second derivative being negative means we're concave down. So when your second derivative at your critical number c happens to be negative, if you're concave down, well, then you've got a max. And if your second derivative is positive, well, then you're concave up, you've got a minimum. Notice there's lots of ways that the second derivative test might not apply. So, for example, if the second derivative doesn't exist, well, then the second derivative test really wouldn't apply. If f double prime of c was nothing, if it was undefined, then you couldn't say whether you have a max or a min using that second derivative test. Or if the second derivative was equal to 0, you wouldn't be able to say whether you have a max or a min. So as some examples of that in action, you've got these two functions, f and g, and if you're looking at both of them, if you look at f of x and find its derivative, you find it's equal to 0 when x is equal to 0. And if we look at the second derivative at 0 is also equal to 0. So this is an inconclusive second derivative test. Our second derivative is not positive, not negative, so I can't tell whether we have a max or a min or something else going on. And in fact, if you know the graph of y equals x cubed, then you know that you have neither. In fact, what you've got going on at that point is a point of inflection. Y equals x to the 4, same sort of a thing. If you did the first derivative, you would find that the first derivative is 4x cubed, and it's equal to 0 when x is 0. And if you did the second derivative, you'd find that the second derivative is 12x squared, and that when you evaluate it at that critical number of 0, you get 0 again. So in both cases, first and second derivative were both equal to 0 at the origin. One of them, it was a point of inflection, but for this x to the 4 graph, it's a relative minimum instead. So when you have your second derivative being equal to 0, then that means your second derivative test is inconclusive. You can't draw a conclusion one way or the other. And that means, of course, you're going to need to rely on something else, namely the first derivative test. So that's kind of the big commentary here, is that If your second derivative test fails, so if your second derivative happens to be 0 at that critical number, or it doesn't apply, the critical number isn't because f prime is 0, the critical number is because f prime is undefined, or f double prime does not exist at that critical number, well, then you can use the first derivative test instead. And you may choose to use one test or the other depending on how easy or complicated things might be. You might have noticed sometimes functions are easy to take derivatives of and sometimes they're not. And so maybe sometimes it might look like you've got a function, it was hard enough to find the first derivative, and it looks like maybe the second derivative is difficult to find, and maybe it's really clunky, and it's going to involve all sorts of rules. So maybe you just will stick with the first derivative test. Or maybe the second derivative is really easy to find or would be really easy to evaluate. Well, then maybe the second derivative test is the faster way to go. So let's do some examples. We're going to find relative extrema for these functions, and we're going to use the second derivative test when possible. So for this first function, f of x equals x plus 2 sine of x, I'm looking at this. It's for sure defined for all real numbers. Sine is defined for everything, so is the x part. So over our little interval from 0 to 2 pi, for sure, then I would have defined f of x on all that interval. So let's find out where do we have critical numbers then. Because I know I don't have any places where my function is undefined, and I don't find any places where my first derivative is undefined either. The derivative of x is 1, the derivative of 2 sine x is 2 cosine x, and we have a first derivative that's defined everywhere. So I guess we will only find critical numbers where f prime is undefined, or sorry, where f prime is 0. So 1 plus 2 cos x is 0, or in other words, cosine of x is negative a half. And we know that there's going to be two places where cosine is negative a half. One of them is in quadrant 2. That's at 2 pi over 3. And then the other one is in quadrant 3. And that's 4 pi over 3. So those are our two critical numbers. So right now, second derivative test certainly will apply because we have places where our first derivative is equal to 0. And we're going to see that our second derivative will be defined at both of those places. So when we take our second derivative, the derivative of cosine is, the derivative of 1 plus 2 cosine of x is 0 minus 2 sine x. Remember, derivative of cosine is negative sine. And of course, that is going to be defined at both of those places, 2 pi over 3 and 4 pi over 3. So I can go ahead and use my second derivative test. So first I look at second derivative at 2 pi over 3. Sine of 2 pi over 3 is positive root 3 over 2. So I have negative 2 times root 3 over 2, or negative root 3. So our second derivative turns out to be negative, which means we are concave downward, which means that we've got a relative maximum at x being 2 pi over 3. And then next we look at 4 pi over 3. And for that, sine of 4 pi over 3, sine of 4 pi over 3 is negative root 3 over 2. The 2's cancel. That gives me positive root 3. And that is positive second derivative, so we are concave up. So that means we must have a relative minimum at 4 pi over 3. Okay, let's do a couple more examples. G of x. So I'm looking at this function, and I can see, of course, the inside x squared plus 1. I know that that's going to be as small as 1 or larger. So my square root of x squared plus 1 should always be defined. I don't have any places where the inside would ever be negative, so we're good to go there. If I were to look at my first derivative, and I'm just going to remind myself that when I say x squared plus 1 square rooted, it's really x squared plus 1 to the power of a half. So when I take my first derivative, I'm going to say chain rule tells me half x squared plus 1 to the negative half, and then derivative of the inside, derivative of x squared plus 1 is 2x. The 2 and the half would cancel, and the x squared plus 1 to the negative half, that's just a square root down in the denominator. So again, the square root of x squared plus 1, this thing could never be equal to 0, so I never have to worry about my derivative here being undefined. The smallest it could ever be would be 1, and that would be if x was 0. So I don't have any places where my derivative is undefined. Let's find where our derivative is 0. And that one's a really easy one to do because, of course, if you're letting your derivative be equal to 0, a fraction is only ever equal to 0 when the top is 0, and the top is just x. So when x is 0, the numerator is 0, which makes the fraction 0, which makes g prime equal to 0. So it looks like we've only got one critical number. That's x equals 0. And so now I guess the next thing for us to do is to consider the second derivative. And so for the second derivative, I'm going to look at that and say that's quotient. So quotient rule tells me the bottom will get squared. X squared plus 1 square rooted. When I square it, I'll just get x squared plus 1. The bottom will come up as it is, times the derivative of the top, minus the top as it is, times the derivative of the bottom. And I've done derivative of square root of x squared plus 1 already, so conveniently enough, I know that that would be the 1 over 2 root x squared plus 1 times 2x. So I'm pretty much good to go. I could do some simplifying here if I felt like it. I could do one little bit of simplifying right now, which is the 2 and the 2 I could cancel. And I can combine the x and the x to give me x squared. So I could say that really what I've got is square root of x squared plus 1 minus x squared over root of x squared plus 1 all over x squared plus 1. If this were a question where I was asking you what is the second derivative, I would not stop here. I would definitely want to simplify further. I wouldn't want to leave fractions inside of fractions. However, I'm not doing the second derivative just for the sake of doing the second derivative. I'm doing it because I'm going to evaluate it so that I can use the second derivative test. For my second derivative test, I just need to find out what is g double prime of 0. So rather than spending my time simplifying, I'm just going to evaluate and find out what g double prime of 0 is. And if it's positive or negative, then I can draw a conclusion. So I have everything I need for me to use the second derivative test. I have my function. It's nice and continuous. It's continuous at my critical number. I have only one critical number, that's x equals 0. That's only one place where we have our first derivative equal to 0. And I have a second derivative, and now I'm going to evaluate and find out what is the value of g double prime at 0. So when I put in 0, I'll have square root of 0 squared plus 1. I'll have minus 0 squared over square root of 0 squared plus 1. And then I'll have in the denominator 0 squared plus 1. So that gives me root of 1 minus 0 over 1, which is just 1. So my second derivative at 0 is positive, which means that we are concave up. So that means that we have a relative minimum at x equals 0. Okay, let's do another one just for fun. So another quotient, so quotient rule. Let's see what we get. So the bottom gets squared, m minus 1 squared getting squared gives me m minus 1 to the 4. The bottom comes up, derivative of the top minus the top as it is times the derivative of the bottom. Derivative of m minus 1 squared is power comes down, power reduces by 1, derivative of the inside is just 1. And then a little bit of cleaning up to do here. I can take the m minus 1 that's a common factor out, leaving in the first term a single m minus 1, and in the second term a 2 times m plus 1. And a little bit of canceling. And then just to finish my simplifying, so now I have m minus 1 cubed in the denominator, and in the numerator I'll have m minus 2m, which is minus m. I'll have negative 1 minus 2 more, which is minus 3. Okay, so let's find out where our first derivative is equal to 0. And for our first derivative to be equal to 0, since that's a rational function, it's equal to 0 when the numerator is equal to 0. So in other words, just at that one place when m is negative 3. There's also a place where the first derivative is undefined, m equals 1. That is also a critical number, but I also know that that couldn't be a maximum or a minimum because that would be a place where we have a vertical asymptote. So I know that m equals 1 is a critical number. It is a place where I could change from increasing to decreasing, but it wouldn't be a maximum or a minimum, so I don't really care about 1. The only one that I care about here is minus 3. So I guess next thing to do is find our second derivative. So for our second derivative, the bottom will get squared. So m minus 1 cubed when I square it gives me m minus 1 to the 6. The bottom comes up. Derivative of the top, derivative of negative m is negative 1, minus the top as it is, times the derivative of the bottom. Okay, so now the last thing for me to do is just to clean things up a little further by factoring. I have in both factors, I could take out m minus 1 squared. And that'll leave an m minus 1 times a negative 1 and a minus a negative m minus 3 times a 3. Okay, a little bit of canceling. Cancel, cancel. There we go. So that we now have m minus 1 to the 4 in the denominator. And then just to clean things up here a little bit, so if I were to expand the top, I would have a minus m and a plus 1. I would have a positive 3m. I would have a positive 9. Or in other words, I would get 2m plus 10 in the numerator. Okay, so our function that we have here, the second derivative, definitely it is defined at my point m equals 3. So let's figure out what is my second derivative, or rather at negative 3. What is my second derivative at negative 3? So when I put in negative 3 on in the denominator, negative 3 minus 1, that's negative 4 to the power of 4 is 256. And when I put in negative 3, I'll have minus 6 plus 10, which is 4. So 4 over 256, or 1/64th, which is positive, so we are concave upwards. So by the second derivative test, that means we must have a relative minimum at x equals negative 3, and that's, again, courtesy of the second derivative test. Okay, one little last quick one, f of x. This is a short little function, x to the 4/3. Defined for all real numbers, for sure. You can always take a cube root, and then you can always raise to the power of 4, so no discontinuities to worry about here. And for the derivative, relatively easy to do because it's just power rule. 4/3 minus 1 is 1/3. And I can find that f prime is equal to 0 when 4/3 x to the 1/3 is 0, which is the place where x is equal to 0. So one critical number, x equals 0. And now let's get ready to look at our second derivative. So first derivative, 4/3 x to the 1/3. I guess I'm just going to use power rule again. So 4/3, bring the power down, reduce the power by 1. 1/3 minus 1 is negative 2/3. And so I wind up with 4/9 x to the 2/3 in the denominator. And right away I can see a problem, and this is the problem with me using the second derivative test, is that f double prime does not exist when x is equal to 0. This is undefined at x equals 0. So that means I need to use the first derivative test. So I have a place where my second derivative test won't work. And remember, there's two ways where your second derivative test won't work. One of them is if your second derivative is equal to 0 at your critical number. The other is if your second derivative doesn't exist at your critical number. And our second derivative does not exist when x is equal to 0. So instead, I'm going to use the first derivative test. And reminder for that, for me to use the first derivative test, I pick an x value on either side. So bigger than 0, I'll pick 1. Less than 0, I'll pick negative 1. And then we use our first derivative to figure out, is our function increasing or decreasing on that interval? So when x is equal to 1, in our first derivative, putting in 1 would give me 4/3. That's a positive value, so we are increasing. And at negative 1, my first derivative would be 4/3 times negative 1 to the 1/3. Negative 1 to the 1/3 is negative 1, so we'd get negative 4/3. We are then decreasing. So we decrease followed by increasing. We must be a relative minimum. So second derivative test is nice, but we always have to remember that there are places where the second derivative test will fail for us. And if that's the case, we don't just give up, we use the first derivative test instead.